Throughout this course, we will formulate our filtering, prediction, and smoothing problems using so-called state space models. We will use these statistical models to describe what we're interested in. We call this our state vector, how the state vector evolves over time, and how it relates to the observations that we make. We will in later lecture show how we can use these models to solve the general filtering problem. So, in this lecture, we will look at how we define these models and what's their purpose when it comes to solving our estimation problems. We will focus our attention on discrete time state space models, as it's often enough to estimate our state with a certain time interval. So, discrete time state space model models a so-called state vector, which we denote xk, and a measurement vector, which we denote yk, where k here is a discrete time index in both cases. First, we have a motion or process model, which in its most general form describes the current state, xk, as a function fk-1 of the previous state, xk-1, and a motion noise process, qk-1. The purpose of this model is to statistically describe how the state evolves over time. Secondly, we have a measurement or sensor model, which again in its most general form describes the current measurement, yk, as a function hk of the current state, xk, and a measurement noise process, rk. The purpose here is to statistically describe how we can relate the current state to our observation yk. Additionally, in our discrete time state space model, we also have a prior distribution of our state. This is the distribution of our state at time 0 before we make any observation. With this model, we can describe any general knowledge that we have about our state vector before we even make any observation. So these are the basic building blocks of a discrete time state space model. And I'm sure that you have come across this type of model in other courses that you have studied, for example in control theory. What we typically also assume, which is not evident from what we see here, is that both the motion noise, qk-1, and the measurement noise, rk, are independent of all other noise vectors. This means that they're not only independent from each other, but also independent over time. So the measurement noise at time k is independent from the measurement noise at time k-1, for example. And these assumptions also ensures that the Markov property holds for the state space model. Alright, so let's look into more detail regarding the motion and measurement models. We start with the motion or process model. I should mention that throughout the course I will probably use both of these terms interchangeably. The term process model stems from control theory, where one in general wants to control some process, and then one needs a model for the dynamics of this process, which is then called a process model. In terms of, for example, estimating the position of a vehicle, the process model in this case should then describe the dynamics of the vehicle, and thus the process model will describe the motion of the vehicle. A more descriptive name in this case is to call the process model for what it is, and that's a motion model. So, in sum, the system dynamics is described by this model here, which we refer to as a motion or process model. There are a couple of things that are interesting to note here. Firstly, the motion model describes the state evolution, and an equivalent view of this is that it describes the distribution of the current state conditioned on the previous state. Often when we talk about the motion model, we have both of these representations in mind, both the equation form here and the density form here. They are equivalent views of the motion or process model. With this interpretation here, we assume that we have perfect knowledge about where the state was one time instance ago. That is, we have no uncertainty about this. What the motion model then describes is the distribution of xk conditioned on the previous state. So what are probable states in the next time instance? As such, the motion model allows us to connect states over time and help us rule out unreasonable trajectories. That is, if we want to estimate the position of an object over time, we typically have physical constraints that limits the movements of this object over time. So if we assume that we are tracking the motion of some object over time, we often want this trajectory to look fairly smooth due to physical constraints. often something like this and not something like this. And we use the motion model to rule out these unreasonable trajectories. So let us look at this from the perspective of an example. So if the state at time k-1, for example, describes the position and velocity of a vehicle. So it describes the position and velocity of this vehicle. So knowing this, the aim of the motion model is to describe the state at time k, or the distribution of the state at time k. In this case, it seems reasonable to assume that the vehicle continues to move as it did at time k-1, which would give us a state something like this. However, we cannot rule out that the vehicle doesn't make any changes to its velocity vector by, for example, turning the steering wheel, stepping on the brake, or pushing the accelerator pedal. This would mean that we need to allow for the predictions to look something like this, if, for example, the vehicle has turned somewhat. But we still need these deviations to be reasonable, and not as we see in this example here, right? So it's unreasonable that a vehicle which has a velocity like this would, in a short time instance, have a position and velocity like this. And this is unreasonable both from a vehicle dynamics perspective and also from the kind of changes that one can expect a driver to make. So the motion model considers two aspects: the dynamics of the system, which is usually described using physical models, and the uncertainty regarding what can change between two time instances. And how much changes we allow is modeled by the motion noise process, qk-1. These two aspects together make up a statistical model of probable state at the current time given the state at the previous time instance. And in this case, we could get some distribution looking like this. So states in this region are probable. States outside this region are improbable. And this is an illustration of the motion model. And with this motion model, these types of states here would be very improbable. The other piece of the puzzle is what's called the measurement model, which describes how the measurement relates to the state vector using this equation here. Also, in this case, we have two names that we use interchangeably. We call it the measurement model or the sensor model. We should note that, as with the motion model, the measurement model has an equivalent probabilistic interpretation, as it describes the distribution of yk given our state xk. So p of yk given xk. And we recognize this distribution here as our likelihood function. So the measurement model actually defines the likelihood function in our estimation problem. As such, when we talk about the measurement model, we sometimes mean the likelihood function, as they are equivalent. As with the motion model, we have an equivalent probabilistic representation of this equation. The other thing that we should note is that we use the measurement model to relate data to our state vector. And it helps us to use data to learn more about our states. And in most cases, we cannot observe the state directly, and even if we could, our measurements are then corrupted by measurement noise. So let us look at this from an example where we have a host vehicle that is equipped with some sensor, let's say a radar in front of the vehicle, which has this field of view here. This radar will give us noisy observations of this vehicle here that we are interested in positioning. So in this case, our state vector xk represents the position of this vehicle. And yk then represents the radar returns that we get from this vehicle. One way to view this measurement model here, or here, is to view it as a generative model that we, in this case, can use to simulate radar returns from this vehicle here. If we have designed our measurement model HK accurately, we should then be able to simulate radar returns from the vehicle, which both describes where on the vehicle we expect the radar returns to end up, as well as the statistical fluctuations in the returns, which are influenced by our measurement noise process, RK. If we use our measurement model to generate independent samples of YK, it could look something like this. And ideally, if the measurement model is accurate, if we were to collect data from a radar that is viewing the vehicle like this, we will get something similar. However, we should bear in mind that these are just models, and we will never fully cover all aspects of reality. What we aim for is to cover the more important aspects that also affects our filtering results. There is also a slightly different variant of our time discrete state space model, where we include a known input signal, uk. As the signal is assumed to be known, we treat it as a deterministic variable in our models, so we simply add it in our equations here as a time-varying parameter in our models. For the density representations, it is common that we write it like this, with a semicolon here, to indicate that uk is not a stochastic variable, but we should rather view it as a time-dependent parameter in our models. It is common to use this type of input signal to include control input signals into our models. But it may also be used to include accurate measurements directly into our models. For example, if we have an accurate accelerometer with negligible noise, it would perhaps be a better idea to include it directly in our process model through this known input signal uk than it would be to use it as a measurement. And the reason is that if we use it in our motion model, we can then hopefully get better predictions here, which would help us to describe the measurements with less uncertainty. Here's a self-assessment question related to the use of the motion and the measurement model.